My name is Hassan Faris, Application Engineer Fluorescence and X-ray Fluorescence from HORIBA, France. I have a PhD in physics since 2016. I have worked in glasses, Doppler Earth for erbium doped fiber amplifier. In Tunisia I get it, and then I went to Brazil for a postdoc for 2.5 years, and then in France for 1 year, and then as associated professor in France for 2 years, and then I stopped everything and I said I would change the work. So I joined HORIBA in 2023. I'm there since I think almost 2 years and 10 months, almost already. And so my job, in fact, is giving training, basically sample analysis, demonstration for customers, and especially customer support and sales support. So our colleague Bilal, who is responsible here in Lebanon and other territory, I think. So if he have any question or anything, so he ask us, and he ask the product specialist and the application engineer. So we try to give them the answer regarding to the customer what they want. I don't know how to use this usually. Yeah. So today I will present for you a short presentation regarding the FLQM. I will start by explain for you a lot of things, why it's called FLQM and so on. So FLQM mean Fluorolog, stand for Fluorolog Quantum Master. HORIBA, it's a company, a Japanese company, purchase a lot of companies in the world, and from this company they purchase Specs, which is here. And Specs is an American company. They produce spectrophlorimeter at that time, and Raman, okay? And then also they purchase Juba Yvon, it's a company in France. They produce also fluorescence, monochromator, and Raman. So there is a problem. They said, okay, we cannot give produce to two companies from the same company. So they split it in two. They said, okay, United States, they will focus in fluorescence, OSD system, and so on, and monochromator, and France, they will focus on Raman. So this is how we'll start the story. And in 2003, there is a company called EBH in Glasgow. They produce electronic for TCSPC, time correlated single photon counting for lifetime measurement. So they purchase it, and then they join to HORIBA. And before, so we have a different system. We have Fluorolog Specs, we call it, but it's just for steady state measurement. And then when they purchase EBH, they add also TCSPC for lifetime. And then they produce Fluorolog-2, Fluorolog-3, Fluoromax, and so on. So here there is a problem. There is a lot of systems with different software to control the system. So they think about a new strategy. They said, okay, we need a new concept, a new system that can be controlled with one software. So we are able to do steady state phosphorescence and TCSPC. So for this, they purchased PTI. It's a Canadian company, and Carrie Davis is from Lebanon. Our global product manager is, I think, from the south, from the north of Lebanon, from the south. You know him, Carrie Davis. And he will love visit Lebanon. Yes, he's from Lebanon. He's our global manager of fluorescence, based in Ashaya in New Jersey, in New York, near to New York. So we purchased this company, and they have at that time a system called the Quantum Master. Sorry. So we have now Fluorolog-3, Quantum Master, and so they said, okay, let's combine both systems. So Fluorolog-3, they keep the best things from Fluorolog-3, they add the good things from PTI, and this is why we have the new generation called FLQM. So this is the story. So with FLQM, we have a software called Felix. We are able to control all the parts from this software. So we are able to do steady state phosphorescence and TCSPC using one software. Okay. So this is the story, and this is how it started, and this is why maybe you have two systems a little bit different. Fluorolog-3, there is a different monochromator inside called Gemini. With Fluorolog Quantum Master, it's a new generation of monochromator, and also the grating inside is different. Okay, so the difference also that before we have just one motors to control the slits. Now we have three. So we can control each slits by individual monochromator. So this is the story. Maybe it can explain a little bit this change, and yeah. So why Fluorolog-3 they choose to change from Fluorolog-3 to FLQM? Simply because the market now need a new system, very modulator. So this is why they take the decision to change everything. So here, this is we start from Fluorolog-1 from Specs company, Fluorolog-2 from Specs company, Fluorolog-3. Then we introduced HORIBA, so Joubert-Yvon company from France, that we used the grating from them, and now we have a new generation called Fluorolog-QM. So this is the story. I will go over just briefly. This system is very, very modulator. Is the most modulator system in the world. This is the first thing. Also, is the most sensitive system in the UV-Vis region. And for example, we can add up to 4 excitation sources, 3 in the double monochromator and 1 in the sample compartment, and we can go up to 6 detectors if you have the full configuration, even more than 6, I would say, because you have the housing of the PMT outside, so you can take off the tube by yourself and you can add whatever you want as in the future. So fluorescence, the system is used in different fields, chemiometry, polymers, material science, cosmetic, and so on. So you know already all the things. With Fluorolog-QM, we can do a lot of measurement, fluorescence, phosphorescence, lifetime kinetics, up conversion. They told me that you already purchased the laser for that. A lot of things, polarization, EAMS measurement, even you can correct the inner filter effect. I will explain for you later, and so on. So if you go to Google Scholar, you will see that HORIBA is the leader in fluorescence. For sure there is other competitor, but HORIBA, I did my PhD with HORIBA, I did my postdoc with HORIBA. So when you are in front of HORIBA, you know that the system you will be very confident. You need just to know how to use it. This is the only thing you need to understand. So if you go to Google Scholar and you write Fluorog or fluorescence, you will find thousands and thousands of publications from HORIBA Scientific. So yeah, let me. This is, as I said, is the specification of FLQM. So as I said, we have a high sensitivity. We can reach 35,000 count. The noise to signal ratio, the signal to noise ratio. Sorry. We can start from UV, deep UV, from 180 till 5,500 if you have the infrared detector dedicated for that. And we have a new generation of software called Felix, so it's very user-friendly. And for the TCSPC, it's a plug and play, so you need just to change the delta diode if you want, and so on. So we are using a new generation of lamp. Before we are using the 150 and also 450 watt. Now we have a new lamp called the 75 watt. But give the same as 150 in terms of sensitivity and even more, because it's a new design. I will explain for you later. This is, for example, few configuration that, let's say, we have. So here, for example, Fluorolog-QM 1.1. 75 means the power of the lamp. 1.1 is we have a single monochromator. Here, for example, we have a single monochromator with the PMT and the xenon lamp, and the sample compartment here. So another thing very important, the sample compartment of Fluorolog-3, Fluorolog-2, FLQM is the same. So if you have accessory from Fluorolog-3, you can use it in FLQM, any accessory, okay? So here a few configuration, double one and double and so on. Is dedicated. In fact, the configuration is regarding your application. For example, a single monochromator here is just for liquids, to be honest. So if you want to do powders, solids or thin films, is not the best configuration because the stray light will be very, very high. So we proposed the double monochromator, especially in the excitation, to decrease the stray light, to have a stray light reduction around 10 - 10. Here is 10 - 5. So if you want to analyze powder with the let's say a very low quantum yield, you will get a lot of trouble here. So you need filters. So I will go through this because it's not so important. I think this is the configuration you have already. This one, okay? So you have a xenon lamp, just a xenon lamp. You don't have a flash lamp for phosphorescence, no? Xenon lamp. So this is xenon lamp, a double monochromator. So we can see here the first monochromator, the second, and the intermediate slits. That is just for slide rate rejection, please. It's not to increase or decrease the sensitivity. We put it here just to increase the slide rate rejection, okay? And you have a double in the emission and of course a PMT 928 or whatever you want to put there. So yeah, this is a configuration that I have in the lab. So you have a flash lamp. So you can, in the future, you can upgrade your system. You can add this flash lamp. It's dedicated for phosphorescence measurement. So we can acquire phosphorescence and also long lifetime measurement and so on. I have a PMT 928 and EGA DSS detector and a Mamatsu detector here. So as you can see in your configuration in the future, you can add another detector here. And also don't forget that the tube, the housing, you can change the tube by yourself. And this is of course the delta diode, plug and play and so on. So to be honest, this is the one of the most, let's say, expensive configuration we have. So here we have 4 sources, and this is super continuum laser. So you can use the super continuum laser as excitation source, but it's very, very expensive and very, very important for especially the lifetime. You don't need to purchase a lot of delta diodes. With one laser, you can do whatever you want. You need just a monochromator here. So there is a flip mirror, so you can switch between the laser and the xenon lamp by clicking in the software. So this is another configuration. It's the most expensive one. It's in HIA in New Jersey. So here we can see that we can go up to 5 detectors, 4 3 excitation sources and so on. But we can also add another detector here if you want. So it will go up to 6 detectors. In the future, if you want to upgrade your system, one of the solutions is you add another monochromator. If you want to go up to, for example, people who work in infrared, really far infrared, they purchase a new monochromator and they add the EGA detector here, because you need to add also some azotes. So this is why in some port you will find some injection gas to take off the water or something like this.
Maybe I missed it. I had a phone call.
Yeah.
You said you have a wide emission laser.
Yeah, this is not we have, but you can purchase it here. Super continuum white.
Okay.
So
this will take as if you have all the LEDs.
You don't need delta diodes. Yeah. It's one laser. You can use it from 400 to 2,400 nanometer. It's mean the laser is one light,
okay,
but with the monochromator you will choose your excitation. So instead of
how fast is it?
Fast. How expensive is it?
Okay.
Fast is it's like the lamp, but it's very expensive. I think I don't know. Do you have the price list? But this is one of. You don't need a lot of delta diodes. You need just one.
Okay. And
also you don't need a lamp if you have this. You fix your excitation and. So this is this is another configuration. So yeah, another thing, you can even add a microscope to acquire the phosphor measurement also. There is 2 ways in fact, or you go through the sample compartment, and like this you can correct the excitation because there is a photodiode. Or if you don't want to lose the signal, you go directly from the monochromator excitation. You need to add this flip mirror here. So you can take through a fiber the excitation light, and then you go back to the monochromator through the same optical fiber. But there is another way. There is a platform, you can put it inside here, but you lose a lot of light. This is the best way. So just to show you that the system is very, very modular, and I think I finished with this. I prefer starting with this. So I know that all of you know fluorescence, but let me start from the beginning, please. Maybe there is a new student and so on. Anyone have do you know phosphorescence, photoluminescence, sorry. The word photoluminescence first. What's the meaning of photoluminescence? Do you have a Raman spectrometer here? Yes, sure. Okay. Usually, sometimes you will see in the paper the word photoluminescence. Okay? And sometimes you will find fluorescence. And sometimes you will find phosphorescence. So we call it PL, photoluminescence. This is general word and for physician. I was thinking that I'm using this word before. Okay? But photoluminescence is the general word, and we can split it in both fluorescence and phosphorescence. So what's the difference between them? I was a teacher.
Phosphorescence is in triplet state, بينما fluorescence is from the singlet state.
Thank you very much. And what's the meaning in terms of lifetime?
Phosphorescence is higher in lifetime compared to
Very
fluorescence.
nice. So fluorescence is very, very fast event. So this is why we're using TCSPC to calculate the lifetime. And phosphorescence is a very long event, and this is why they go through triplet state. So for fluorescence, it's like this, tag, tag. Phosphorescence, you need to go through triplet state to obtain the steady state. So for sure, it will be very long event. So here, very fast, it means you can go from picosecond to few microsecond, basically, I would say 10 microsecond. So here we are in the phase of fluorescence. So if it's more than 10 microseconds, so it's phosphorescence, okay? It can go even more than millisecond. So this is the difference. So don't be afraid when you see this word photoluminescence. Basically the people, they use it in Raman because they don't know the lifetime. So they use the word photoluminescence. It's a general word, but when you have the possibility to calculate the lifetime, so we can choose or phosphorescence or fluorescence. So this is just to explain for you. And sometimes when you see in publication some very bored emission using a Raman, don't be surprised when you will do the same with the FLQM. Here it's very bored because they have different grating, different optics, and especially they are using one wavelength excitation, and it's a laser. But in FLQM, or even if you use a delta diode, it's not the same like Raman. So it will be a little bit, you will find a little bit of difference. It will shift a little bit, maybe. It will be more bored, especially here on the Raman. Just to explain for you, okay? I don't know if it's... So this is just to tell you the difference between them and why we call it phosphorescence, why we call it fluorescent, and why we are using TCSPC to measure the phosphorescence. And we are using other technique to measure, fluorescence, and we are using another technique to measure the phosphorescence. So you know that we have excitation, we have emission, and we have the lifetime. So just to explain for you that the difference between excitation spectra and absorption, do you know what they mean? What's the difference? Excitation spectra, absorption spectra is the same. The only thing you need to know that we are using a different detector. Absorption, we collect the signal at 180 degrees using a photodiode, okay? And excitation spectra, we are using a PMT, and we collect at 90 degrees, okay? But it's the same. Don't be surprised. It's the same, and you need to find the same. Excitation, if you use the UVV's spectrometer, and excitation spectra from the PMT, from the FLQM, normally you will find the same. The only thing, sometimes you will find different peaks, small peaks that appear. Why? Because the sensitivity is not the same. The PMT is much more sensitive than photodiode, and this is why sometimes you will obtain, for example, for dyes, something like this, and with the UVVs you will find something like this. The mean peak is the same, but maybe you find a little bit of difference. It's the same. And best thing also with FLQM, there is you can do also absorption spectra if you have the accessory. I don't know, Bilal, if you tell them this. There is an accessory There is two, in fact. There is one, it's a photodiode that you put in the sample compartment and you can collect the absorption spectra, or there is a small accessory. It's not so expensive, and even now I think HORIBA, they propose it for free for the new user. If you can, yeah, you can ask it. I think it's a small accessory that you can put the cuvette, and then you can collect absorption. You need just to put the monochromator at zero position. It will be like a mirror, so you can collect the absorption through the lamp, the profile of the lamp. So just to tell you this, okay? I know that before no one explained for this. So here, as I said, we have excitation spectra, lifetime, and emission. And this is what define your material. These three things: excitation, lifetime, and emission. So the difference between the excitation spectra and the emission, sorry professor, I will go. So when you hit the ball, so you will hit it with energy, but when it touch the thing, so you will get back your ball, but with less energy, so you lose in energy. And this is why we have this stock shift. So this is what explains this loss in energy. So the stock is normally between 10 nanometer to 15, and this is why when you excite, for example, at 350, you need to start from 365 to avoid the scattering, the relays. Okay, so this is why also you need to shift your emission spectra. You should not collect the excitation and the emission, from the. You can, but you will saturate, or you put a filter to cut the signal. Okay, and this is the only way, the only measurement that we use to collect also the excitation part is for the quantum yield measurement for the integration sphere. You need to just to be careful about the saturation and so on. Is it clear this? So the emission is shifted. You need to start from 15 nanometer. And as I said, you have three molecular information: excitation spectra, lifetime, and emission. Okay? This is what define your if you want to characterize your samples, you need this three information. Okay? So as I said, you need to start from you need to shift your spectral range by 15 at least to avoid the excitation, and you need to stop 15 nanometer before. Do you know why? If you don't have optics, you need to stop before the double harmonic. Okay, so you have lambda excitation, but also you have two lambda excitation. So you have this relays, and you have the second. And to avoid this, you need to stop here, 15 nanometer before, or you put a filter, a high pass filter in the emission part. I don't know if you know the difference between high pass, band pass, and short pass filter. So there is a filters also to avoid this. If you want to acquire for longer wavelength, be careful. You need to stop before 2 lambda excitation, and also is the same in the excitation spectra. If you want to see the excitation spectra of emission around 500, so you need to collect from 480 to 165. So we need to avoid also the second harmonic from the other part. So this is basic optics. I think professor, they understand it better than me, so they can explain for you. Okay. So now let's go to the sensitivity of the system. This is just a few things I would like to explain. So the first thing normally we need to do is to check if our spectrometer is okay or not. Okay, and there is steps to follow. Fluorolog-3, you need to control the excitation monochromator is calibrated or not. So you need to collect the excitation. So the first thing you need to take care is when you will start the measurement, maybe once per week, you need to check your system if it's calibrated or not, like Fluorolog-3 before. So we start with the monochromator, excitation monochromator. We need to check it, and the emission monochromator also we need to check it also. Okay. So to do this, so simply we use to control the excitation monochromator, we need to check the profile of the lamp. Okay, so we simply do a measurement. We don't care about the PMT. We can even close it. Okay, we need just to see the profile through the photodiode lamp, photodiode detector. Just to explain for you, we have 3 detectors. We have 2 detectors. Let's say this is the PMT. This is the monochromator. So this is the PMT, and this is the excitation lamp, and this is the sample compartment. Here you put your sample, and this is this. But you have a photodiode here that will collect 8% of the light from the light, and she will correct the fluctuation of the lamp automatically. Okay, so if there is any fluctuation, maybe this correction you will not see it, but it will be corrected automatically. So we use this photodiode to control the excitation monochromator, and to do it we simply collect the profile of the lamp. We need to find spectra like this, and this is the profile of the lamp, and usually we need to see the peak around 450 plus minus 1 nanometer. So if we find it at 400, for example, 56, okay, even 456.5, it's okay. If it's a little bit shifted, let's say we find it at 458, you need to calibrate it. In FLQM before it's easy, Fluorolog-3 it's easy. Now with FLQM it's a little bit complicated, so Bilal he can do it by remotely. You need to change a little bit in the setup, and so this is the first thing you need to see. But also the profile of the lamp can give you idea about the excitation, when I can open my slits to avoid the saturation, when I can close, and so on. So if you see here at 250 we have less energy. So for sure when I will measure there, when I excite there, I need to open my slits more. Here I have the maximum of the light. So here if I have excitation around 460, so I need to close it, because I know that I have a lot of light there. So also this profile can give you idea about when you can open your slits or not. Okay, the same thing here. I think around 700 you have less energy, so the idea is to open more and more your slits to get more energy to have emission, better emission. So there is a lot of things you need to understand before you use, to understand how to really guarantee good results. So this is the first thing. You need to check the profile of the lamp and check the excitation monochromator if it's calibrated or not. Second thing is the emission monochromator, and for this you need to do a water Raman. I don't know, Murad, Bilal, you know it, water Raman. Yeah. So the water Raman is this cuvette I have here. Usually I bring it with me. So you can use any water, but it's not it will not give you the right the right sensitivity. This is from Starna, so we purchase it also to see if the system is good or not. So there is 2 things to check with this standard. That's emission monochromator and especially the sensitivity. And to do this, you can follow this setup. So you excite at 350. You collect from 365 to 450, and you need to find the maximum at 397 nanometer plus minus 1 point or 1 nanometer. So if it's okay, it means your monochromator is calibrated. You can use your system. Okay. Last thing you need to check is the sensitivity of your system. How much is sensitive? If sometimes you don't know. Unfortunately, we don't have we don't know how much we use the lamp. So sometimes we lose this sensitivity, and it means you need to change your lamp. Okay. So it's easy to see the sensitivity of your system. You need just to calculate the noise, signal to noise ratio, which is the intensity at 397 minus the intensity at this noise, 450, divided by the square of E40, 450. So we guarantee A good system need to have more than 20,000, let's say. Okay. If it's less than 20,000, means it's time to change your lamp. You can use it, but maybe for a very, let's say, not fluorescent samples, you will find the trouble. I mean, maybe you will not be able to see a good signal. But if it's less than 20,000, let's say 18,000 to be, you need to change it. Okay, the lamp. Normally it will be stable at around 18, sometimes 25. It depends to the. So there is different thing. Or you lose the alignment, so you need to align your lamp, or you need to change your lamp. Okay. Is it clear? Do you have any question?
How to do the alignment for the lamp?
There is 3 points.
Yeah, I know, but you have to look at the signal live.
Yeah, in live. Yeah, you need to
Have the option.
water Raman. You need to open just the slits, and you see if you increase the signal or not. It's like the old one. You know there is the. In fact, you can see your signal in real time. You can see the signal in real time. I can show you later, because there is in the software in the button, you can see the signal of the PMT in real time. So you increase when it's increased, it's okay. When it decreases, mean you are losing the alignment. It's easy, don't worry. So also this water Raman give us indication about the electronics, if it's okay or not. So, for example, if there is a lot of let's say a signal, it means the quality of the optic is not good. Don't worry, I will give you the presentation after. I already give it to you. So, but usually this is how. So we have two methods. If you are using a CCD detector, our competitor they use this, but it's wrong. You need to use this one. So, yeah, this is during the installation. We guarantee 35,000. Let's say more than 30,000, and so on. So why we reach this high sensitivity? Because we are using mirror instead of lens. If you use lens, you bullshit your data, to be honest, because you will not be able to fix the light in each wavelength in the cuvette or in your sample. So HORIBA, as I said, is the leader in the Joubin Yvon. It's a French company, and they are the best of optics. So even we produce for space, NASA. We have this is one of the biggest grating we produce it. I think we have 2 meter by 1.5, and this year we produced 2. It's very, very expensive, this grating. It's almost 2 million euro. So if we purchase just 2, if we produce just 2, it's a good. So HORIBA, Joubin Yvon at France, they are the best in grating, and even our competitor purchase from us grating like Agilent, like Shimadzu, and so on. So as I said, FLQM, we can do steady state, excitation spectra, emission. Another thing, as I said, everything is corrected with FLQM, especially the fluctuation of the lamp. But also you need to understand, because they told me that you find some shift between Fluorolog-3 and FLQM, but I will guarantee for you that FLQM is better. You need just to know how to use it. So this is about the extension in the future. Phosphorescence, you need to add phosphorescence lamp, so you can be able to acquire the longer lifetime. Near infrared, if you want to put whatever Amamatsu detector or our detectors, call it the DSS, EGA detectors. You can add a microscope, you can add a T-channel, I mean a double monochromator from this side, or also laser, continuum laser, and so on. Do you have an idea about the quantum yield? Do you have integrated sphere before and so on? No? You don't know? Okay. Yeah, there is a few things I would like to explain. So how it works, the FLQM in real time. So you have a lamp, you have a grating, okay? And this is the lamp. So when you excite, in fact, when you open the sleeve or you excite, you will send all the spectra, in fact. It's not one wavelength. So when you said to the system, okay, I will excite to 350, in fact, you are moving the grating will be moved to this position to give you the 350, okay? So in fact, you send all the light through the grating, and the grating, you will decide through the grating which excitation you will send. I have a picture that I took it from in Sweden, I think. Yeah, here. This is how it looks, the system from inside. You see? So you send all the light. You send all the light. And when you move the grating, in fact, you are moving this light to the slit. Okay, so this is how it works. Okay. So you have the full spectrum, and you said, okay, I will excite at 350, so you are moving this light to the slit. In fact, you see, this light will move until you reach this position 350. And then you have a double, the second slit will just take off the stray light, because when you collect 300, when you said 350, in fact, it's not one position, but it's a bored band, okay? So the second slit will decrease this stray light, okay? And then he will send it to the second monochromator, where he will fix it also at 350, and like this, you will decrease this stray light as the stray light to the maximum. So this is how it works, okay? For sure, no one talk a lot about the grating, but this is the most important thing in spectrometer or in spectrophotometer. So I don't know which one you have, but you need to know that there is three things to take care about: the lamp, the grating, and your detector, okay? So the lamp, as I said, from the photodiode detector, you can know where you are good or not. Basically, we can start from 185 to, I don't know, to near infrared, maybe 900, but be careful, as I said, you need to check the profile of your lamp. So this is the first limitation. Then you have the grating. I don't know which grating you have, but usually you have a grating with 1200 line gloves, blazed at 400, for example, or 300, this one. 400. And this is, we call it lambda blaze. And this is the most important part in your FLQ, Fluorolog, or any spectrometer. What's the meaning of lambda blaze? Mean the maximum efficiency of your grating is there. Okay, so we don't need a correction when we are there, but you need to apply it for sure. Lambda blazes mean you are able to excite, if it's in the excite part, from 2 lambda blaz to 2 lambda blaz. So this is where you can excite. You can excite before, but it's not a corrected data. So if we multiply 400 by 2, 800 divided by 3, it will be around how much? 800 by 3, 200, 270. It's 300. It's a blaz, 300 a blaz. It's not, it's 300, I'm sure. I'm sure it's 300. 600 divided by 3, 200. From 200 to 600 in excitation, you are good, okay? You are good. So if you will acquire excitation spectra, you are very good from 200 to 600. Okay, you can excite. This is for the excitation spectra. I don't speak about the emission spectra. Emission spectra is another case, okay? But just to tell you, excitation spectra from 200 to 600, you are very good, okay? Of course, I will explain for you later what you can do, what you need to do. So this is the first limitation. The lambda blaz or the grating is the most important part for me in your spectrophotometer. You need to understand what's the meaning of 400. It's not for nothing is there, okay? So at 400 you have the maximum of the excitation, and you are limited by 2 lambda plus and this the tiers de lambda plus. Voilà. Donc from this to 2 lambda plus. The same thing in the emission part. So in the emission part you have a different grating. You have 400, 500, 700, 1000. I don't know which one you have, but it's the same thing. So lambda plus define your efficiency, the efficiency of your grating in the emission part also. So let's take the emission part. You have the excitation, you have the grating, and also you have the detector. And the detector is from Amamatsu. And if you write in the Google Amamatsu 928, you will have something like this. Okay. The maximum of the efficiency will be around, I think, this is regarding the lamp. It's not so important. This is the grating slits. Yeah, this is application note regarding here. So there is different detector, but let's say 928. So we see the sensitivity curve, which is this one, quantum efficiency. So let's say from 200 to here, this one, from 200 till 700, you are good. From 700 to 900, you start to lose your sensitivity. It's not the system, but it's the detector. Okay, so this is also a very, very important thing. This is, you will understand when you will correct, when you will obtain, let's say, a problem when you correct also. So from 700 to 900, if you apply the correction, it will be a little bit complicated to explain, but I will explain for you. So this is the profile. You need to understand, we need to correct. We correct the fluctuation of the lamp. We have the photodiode for that. Don't worry about. We correct the optics, the grating. We have the correction file for that. And also we correct this thing here. How it works, the correction. This is the profile, okay? If you want to correct the optics, you need to multiply by something, the opposite. So here, almost 100%. Sorry, this is 1, let's say 100%. So here your detector is good. Here is not good, here is not good. So you need to add something, you multiply by a correction file, which is the opposite of this. It will be like this, okay? In the end, you will obtain 1 or 100%. So if you see here, I correct a little bit, but here I correct more, and here I correct more and more and more. Almost I correct all the things here. So from 800 to 900, I don't want to say this, but there is no meaning to measure it there. Yes?
Sorry, I haven't used it before, so I just have to
Yeah, you need to apply it on the software, and this is why maybe you are not finding the same results, because you are not applying this. Before it was automatically in Fluorolog-3, but now you need to do something in the software to do it, and this is the missing part in your data. This is why I told you I will explain for you. Okay, so to be honest, from 200 to 800 to 700, you correct, for sure you will correct. But from 750, let's say, to 900, if you have emission there, don't try to do it. There is no meaning. You will obtain a lot of correction. And for this, there is other detector. It's the limitation of the detector, not the system. Okay? The difference between Fluorolog-3 and FLQM in this point, it's here. FLQM is better. And from 750 to 800, Fluorolog-3 is better. And why? It's normal. It's a choice, okay? We are using a housing. We cool it down until minus 20 degrees. So when you cool it down your detector, you will reach a high sensitivity in the UV region, but you will lose the extension part. You understand me now why? Fluorolog-3 is without cooling, so it will be very bad in the visible range. Even it's good for you, but believe me, FLQM is better. But you will be able to go more, 50 nanometer more, to acquire the signal. This is the only difference. But for the UV region, FLQM is better, and this is why we reach 30,000, 35,000. So with FLQM, you'll not be able to reach it. So if we see the correction file, maybe it will be like this. So as I said, this is the profile of the detector. So the correction file will be like this for FLQM, and will be like this for Fluorolog-3. Okay, from 750 to 900. Not to 900, even Fluorolog-3 will not work with 800. So 50 nanometer. FLQM is better, but before, this is a Fluorolog-3. This is FLQM. So if you see here, the sensitivity here is better. We correct less, we have more signal. We correct more, we have bad signal. So this is the only difference. So FLQM is better in the UV region. Little bit. To be honest, I don't care about this because you need to change the detector. Even with the Fluorolog-3, you need to change the detector. But here we correct more. Why? Because we are not using the same design of the detectors. Is it clear? So before in Fluorolog-3, you don't need to apply this correction. With Felix, you need to use the correction in the software. And maybe this is why this is the missing part that you didn't use it during the measurement. I will explain for you. So when you have a blazing lambda plus around 400, imagine that you are measuring, for example, a system that he have emission, a sample have emission 420. So this is the signal without correction, and this is the signal with correction. So when we correct, we increase the intensity, in fact. Okay. Blazed at 400, emission at 420. We need just you will increase just the intensity. But now, if the emission is around 500, you will increase the intensity, but also you will shift your emission because of this correction file. You need to correct this, and when you correct it, you will shift your emission, and the shifted one is the best data. So it depends to the lambda plus. So this is why you have a shift. Before 400 or at 400, even if you correct, you will just increase your emission, or you will lose a little bit. It depends. In fact, we increase a lot. But at 500, you will also be able to shift. So the corrected data and uncorrected data, it will be a little bit different to each other. But you need to correct. You must correct. And this is the real data. You must correct your measurement. Otherwise, it will be wrong. Okay? Is it clear? Another very, very important thing. So this is about the parts and so on. No. Do you know the linearity of the detector? Here, you will reach the saturation around 10 million. Over 10 million, you're saturated. Okay, even if the software don't tell you this, but you are saturating the signal. So the maximum of CPS count, it will be 10 million. 10 minus 10 à la puissance 6. This is what we said. Okay, 10, 6. So, in fact, the detector is like this. Okay, you are linear from 0 to 5 million. 5 million. 10. J'ai oublié comment. 5, yeah. So you are linear from 0 to 10 avoid to measure here. From 5 to
5 times 10 6 is 5.
sorry. It's not the half. 75% to, let's say, for 10 million.
10 to the power 6 is 1 million anyway.
Yeah. In fact, how I measure the linearity, we are from 25 to 75%. 75% of 10 million, how much? 7.5 million. From 0 to 7.5 million, you have a good data, okay? Is it okay? Over 5, you can. Over 7.5, you are not in the linearity of the detector. So be careful. Maybe the detector will be like, he will take in consideration that you are very close to the saturation, he will decrease a little bit. How can I say that? It will be like he will put himself in the safe position. Okay, so from 0 to 7.5 million, it's okay. You can measurement, it's okay. But I will give you my astuce. En français, on dit comment? Astuce. My trick, yeah. I take the half of the saturation. I focus my measurement there. 5 million is the best. From 2.5 to 75, but I prefer 5 million. This is, I know that I'm really good, and this is the track I use it for quantum yield measurement, because it's very, very, very important to work in the saturation. And the saturation, and you need to see the raw data before correction. If you correct, you will increase the signal, so you can even go more than 100 million. It's not a problem. You need just to focus on the raw data before correction, before all the corrections. So don't forget, we have the correction of the fluctuation of the lamp, we have the correction of the optics, and we have the correction also of the detector, which is this one. Don't worry, everything is corrected, including the software, but you will be able to see the raw data. I will show you how, and it's in real time. Okay. I think this is the most important thing you need to understand regarding the FLQM. How to guarantee good data, avoid the saturation, be careful about the grating you're using. You need to know why it's shifted, because with the correction you will shift, and the excitation profile when you open your stis more, and so on. This is what you need to know, in fact. This is the information I give it for you. Is it okay? Now I will go to the TCSPC, time correlated single photon counting, how it works. It's very easy. I think it's the best part of the training. I will show you maybe in the presentation, but for me this is the weak presentation. This is what I was discussing about. Excitation grating blazed at 300 PMT and so on. So this is also.
Before we move on, can I ask a question?
Yes, of course.
Okay, so sometimes when I use the fluorometer, there's a blue or green light that shows up from the lamp in the sample compartment. It shows up sometimes and sometimes it doesn't.
Because you are changing the excitation.
I'm changing the no, I work on the same excitation wavelength and emissions.
Show me later.
Okay.
Because when you are moving the monochromator, you will go out inside the sample, or you open your sample compartment.
When you open the sample compartment, sometimes the light shows up and sometimes it doesn't.
Depends on where the excitation monochromator stops.
Yeah, this is the monochromator. But for example, if I have a powder, and I don't know if my powder is the right position or not, or the thin films, what I do, I go to the emission monochromator, I change the position in the green wavelength or red wavelength, so I will be able to see it. If I am exciting in the UV, I will see nothing. So it's UV or infrared. So I think it's up to, I will show you later, don't worry. Okay. So this is regarding the, there is a lot of, do you know what's the meaning of quantum yield?
The number of photons.
Do you have integration sphere here? No? It's very expensive, but it's very nice measurement to see the efficiency of your material is you will divide the number of the absorption, the absorption by the emission to get the number. We call it quantum yield, and it's the efficiency of your emission in this wavelength. Okay, usually they use it for dyes and so on, and this is very important measurement. Anyway, there is integrated sphere, this one. Side we have spectralon, all to reflect the excitation and the emission together, and there is a calculation you need to do, the absorption, the number of absorbed photon divided by the number of the absorbed emission, and you will get a number, and it need to be less than 100% for sure. So the TCSPC, I will go very. This is all the things. Integrated sphere. We have, this is a sample order for that you can modulate, change the position on Z, so you can avoid also stray light. We call it the front face accessory. This one for powder especially. This is summer. Yes.
This accessory be installed now, for example,
Yeah, you can. Yeah, it's in fact it's, as I said, it's just upgrade. It's not upgrade. It's just accessory. You purchase it and and you put it in a sample compartment.
Yeah, but this is different than the FFRA.
Yeah, it's another thing that improve better and better the signal. You can change the Z even, the orientation and the Z, not the front face. We call it front face accessory, but it's different than the other one.
Okay, so the
That-
other one, this is the mirror that you can flip to
Yeah.
change from front face to right angle.
Right angle, yeah.
So this we cannot install it now. I mean, we have to take the sample compartment back to the factory.
Yeah. Even not in HORIBA, France. You need to send it to Canada. All the sample compartment, but it's just the sample compartment. But otherwise you can purchase this option also. What I'm doing? I don't know. I will show you later. Let's go to TCSPC. Yeah, time correlated single photon counting, we call TCSPC, or the technique to measure the very short lifetime. Okay. So how it work? I love the things, but it's complicated to understand. But I will give you. Okay. TCSPC, time counting, correlate single photon counting. We will count each photon, and for this, to count something, you need what? Chronometer. So you need a chronometer, start, stop, and each time you will measure your photons, the lifetime of your photons, and then you will classify in histogram. So how it works? You have start, and you have stop. So what's my start is the laser, the delta diode. So the profile will be like this. And this is the PMT, is my stop. So I excite with the laser, I send the pulse. Photon 1 here will reach the monochromator, chronometer stop. Okay? So this is my stop and this is my start. And we will measure the time between the start and the stop. And if you go to the system, HORIBA, if you see the cables, you will see that the delta diode controller will be related to the start, and the PMT will be related to the stop. And this is how it works. It's very simple. All the presentation things, but I will explain. It's like this. Then we repeat the things thousands of times, and each time we will calculate the lifetime of these photons, and then we will put it in histogram, and you have the channel number in the software. So there is 512, 1000, and so on until 4000. And we will define these channels. How can I say this? We will put the photons in each. For example, if we find a photon like 2 nanoseconds, there is a gate or channel, or how can we, from, for example, 1.9 to 2 nanoseconds. So I know that this photon I need to put it here. I don't know how much photon you will find in this range, and other photons in this range. You will classify, in fact, your photons each time, and then you will fit. Okay, so we'll obtain like this, and then you fit your decay, and you will find the lifetime, the average lifetime of your emission. This is how it works. Start, stop. You count the photon. You put it inside this histogram. You fit your data and just it. So here you need to be careful about something. When you are in the very fast decay, the contribution of the system is very important. Okay, so this is why we measure the ERF. We call it before we called PRAMP. Now we call ERF, enzyme response function. And this enzyme response function, it depends on three things: the optics, the position of your detector or the delta diode, and what else? Electronics. Thank you so much. The electrons that you calculate, the delta hub or the FIFO, the new generation, the electronics, the delta diode, and the optics. So for a very short lifetime, we need to measure the ERF. Otherwise, it will not be possible to obtain the right data. For me, from 0 to 20 nanoseconds, you need to measure. Over 20 nanoseconds, you don't need, because the ERF is very short. So there is no meaning to measure, to take off this very short picoseconds lifetime from 20 nanoseconds is nothing. So from few picoseconds to 20 nanoseconds, you must measure, you need to measure the ERF. Over 20 nanoseconds, you don't need.
So this is not so as that we are.
Yeah, instrument response function is the PRAMP. Yeah, instrument response function. Is it clear? To another things you need to understand, to guarantee very nice fit, you need to avoid the saturation, not saturation, but the alpha factor. You need to be below 2%. Okay, alpha factor below 2%. You need to fix your count till 10,000 minimum. And you need to respect the most important thing. You need to estimate your lifetime. If it's around 2 nanoseconds, the range need to be at least 20 times more than your lifetime. This means 2 nanoseconds, you need to go until 40 nanoseconds of spectral of range. You need to guarantee all this until the end, you know. And then you need to fit. And when you fit, you need to find a C square around 1.1. To be honest, I don't care about the value. What I saw really is the residual. The residual need to be between -5 to +5. This is what I need to see. When you obtain one, let's say 1.1, even less, it's good. But for me, you need this residual. Yeah, the chi-square, yeah.
Yeah, that square, huh?
Yeah. You need to obtain about around 1.1, but for me, the most important, the residual profile need to be between -5 and 5, and you need to be really like this. Okay, so if there is any problem, it means there is a problem in the, you need to adjust a little bit your fitting. So, alpha factor minus less than 2%, 10,000 at least for a good data, 10,000, and you need to go more than 20 times your lifetime to get a good fitting. When you do this, next step you need to fit chi-square residual part. Okay, and sometimes you do everything, and unfortunately you will never obtain 1.5. Okay, so between 5 and -5 or beds chi-square. What I do usually, I start from, I know that I have one lifetime measurement, one decay, so I start by 2 or 3, and I decrease after. Okay, and sometimes you know that you have one lifetime, so one species there, but when you apply one fit, one exponential, you will obtain always a bad data. So in this case, you go to the second decay. You choose 2 decays, and you will obtain a good data. But be careful about the contribution. Sometimes you will find, for example, 90 8% of contribution of the first decay and 2% of the second decay. So the 2% doesn't exist. It's just to get a good fitting. Okay, is it clear? Do you want me to explain again this one, or I'm going very fast, but if you want me, I can explain for you this in front of the system after. Is it okay? Professor, is it okay?
Yes. But I like the functions and the for the fittings. I mean,
Yeah.
I was surprised to see they have stretched exponential fittings,
Yes.
which are usually not common in fitting.
Which software you are using for the fit?
The one.
Easy Time. Okay. Yeah, Easy Time is the
which
best
I'm
one.
supposed to get a license
Yeah.
a year ago, but it's still on the customs.
It's not his fault. It's a little bit. This is why I was asking. Did you discuss this with Nicola before?
Yeah, he told me that he has a meeting this week with Aramex.
With
Aramex.
Shipping company.
The shipping company.
who? Grahami, Kulwinder. I will call them if you want. A Glasgow company.
Shipping.
Okay. They sent it for you. Yeah, I think they sent it for you, and you didn't get it. Anyway, to be honest, lifetime is not complicated. You need just to understand how it works. Maybe the best thing after to using the samples, I bring it with me. You need to put in your mind the ERF is very important, a very short lifetime, more than 20 nanoseconds. You don't need to do it. To do ERF, you need Lidox for liquids. If you are measuring something solids or something like this, usually what I put a glass. I reflect the light to the glass and through a glass, and I need just to get a sample that I know I will not obtain anything there, and just this. Then alpha factor less than 2%, 10,000, 20 times more than your lifetime, and then the things. So maybe I didn't explain for the student what's the meaning of lifetime and why it's very, very important. So when you acquire emission spectra, you will obtain something like this. Okay, it's a bored band. Okay, I have emission, but I don't know how much species I have. Okay, so what we do a lifetime measurement. So if I find, for example, one exponential as a lifetime, it means I have one lifetime. So I know that I have one species here. If I have 3 lifetime, I know that there is 3. Okay, so if you do trace measurement, time resolved emission spectra, so I know that you will obtain 3 profile like this, because we can build the emission from the TCSPC if we have this option. So when we have this option, so we'll obtain something like this. So here, the first species, this is the second species. So I know that the first lifetime is here, the second lifetime is here, and the third lifetime is here. So this is why TCSPC is very powerful. It doesn't depend on the concentration. It depends just to the surrounding of your samples. So even if you increase the concentration, you will obtain always the same lifetime. Okay. Another important thing, I didn't tell it, sorry. Do you have an idea about the inner filter effect? No? Do you have an idea about the inner filter effect? Especially people who work with liquids, they need to be careful about this.
Stress this point.
Huh?
Stress on this point.
Yeah, because sometimes you will compare yourself with other publication and you will not be able to find the same. Okay, and you will say, okay, I will struggle, and you said there is a problem in my samples and so on. So if fluorescence, it's a little bit complicated, but if you understand it, it's easy to get a good data. Okay, inner filter effect. In fact, people who work with liquids, maybe they will understand this. You know that the fluorescence depend to the optical density, means the concentration, and need to be linear. There is a linearity relationship between optical density and the intensity of the fluorescence. Okay, but in somehow we lose this intensity, and we call it this linearity, and we call it the inner filter effect. So from 0 to 0.1 optical density. When I said optical density is the absorption spectra. Okay, I am linear. Okay, I don't care. I know that if I multiply the concentration by 2, I will obtain the same behavior in the emission. Over 0.1 optical density, we lose this linearity. So we need to correct. Okay, and to correct, there is an algorithm developed by HORIBA, especially for Aqualog Next and Dueta. It's the only system in the world that they do this correction automatically. But with FLQM, you can do it if you required your absorption spectra before. There is an option in the software that you can do it. You can correct the inner filter effect. So what is this inner filter effect? There is two effects, in fact. Inner filter effect 1 and inner filter effect 2. So when you have a concentrated sample, sometimes it's not so concentrated, but as I told you, you need to measure the absorption to understand. If the absorption is more than 1.1, or let's say 1.5 optical density, the light will be attenuated on the surface. This is the first effect. This is one. And the second thing, since there is overlapping between the excitation and the emission, the emission part will be reabsorbed again from the emission, so you will lose in the intensity. So you will lose both here and here. And instead of obtaining intensity like this, you will obtain intensity like this. So you will lose intensity if you don't control your optical absorption sample. This means you will never be able to obtain the same data of someone else if you don't control your absorption. So the inner filter effect is very important for people who work with liquids. They need to be careful. If they don't want to correct, they need to dilute the sample until they obtain 0.1 optical density, less than. If you want to correct, if you don't want to control your concentration, you can acquire the optical density, the absorption spectra, and maybe you can use the software Felix to do it. Okay, so this is very, very important point for the people who work with liquids, and mainly the people who have Fluorolog-3 and FLQM, they don't know a lot about this, but the people who work on biological samples and so on, they take care about this, especially the people who work with insulin and so on, they take care about this point. Okay, so this is, we call it inner filter effect. The attenuation of the light in the surface of the cuvette and the reabsorption of the light due to the overlapping between the excitation and the emission. Is it clear? Ça va? I try my best to go very fast. Anyway, Bilal? Yeah.
Finish?
To be honest, this theoretical part is finished. Another thing. Sorry. Yes. Regarding the lifetime, there is a minimum of lifetime we can detect, and this is also relating the optics, the laser you use, and the electronic. I have a file. I give it to you in the USB there. In your system, I think 118 picoseconds. This is the minimum you can measure. I will check after. I give you this file inside, but I will show you. So why I tell you this? Because if, for example, you do a measurement, you choose two lifetime, and you find, for example, 100 picosecond, it's not right. So you have just one decay because you are not able to measure 100 picosecond. And how we know the minimum of our, the minimum that we can calculate it with the electronic? Yeah, this one. It's very easy. You measure the ERF, your ERF would be like this. You take the half of the width and then divide it by 10, and you will find your minimum of TCS or lifetime you can measure it. Okay, so it's 1 by 10 your largeur à mi-hauteur, j'ai oublié. So we measure the ERF through redox, for example, and then we take the largeur à mi-hauteur, j'ai oublié. For example, here 10,000, you know, as I told you. So you go to 5,000, you take this half of the width, and you will find a value, let's say 1,000 picosecond, for example. You divide it by 10. So you will find your minimum of TCS/PC you can measure. So this is a table, I will give it for you. So here you have a PMT-R 928, so I put 1.2. You have a delta diode laser, or I don't know which kind of laser you have. You have delta diode, so 1.4. You have delta diode laser? Yeah, delta diode laser, so 0.04. And you have a delta diode. Do you have a delta diode? Delta hub, oh, the same. So 0.1, so the minimum is 120 picosecond. So now if you change the PPD, if you change the, if you change not the laser, you have a laser, no? You have a laser or delta diode? But with L, if there is L, it means delta diode laser. If it's without, it's LED.
The old one we do have laser.
Anyway, this is a table that, so in the future, for example, if you want to add a PPD, this is the best electronic, Ash PPD or PPD hybrid or this one. So if you put 0.15, you will be able to reach 5 picosecond of lifetime. You need just 5 picosecond. It depends on the electronic, as I told you,
right,
for the laser and the electronic. Now we have a new one called FIFO. So with FIFO, you are able to go down to 5 picoseconds. And of course the detectors. So there is a PPD, hybrid EPD also. So you can go 5 picoseconds as minimum lifetime you can measure. This is a table, I give it to you to understand, but the best also another way, you don't need this table, you measure your ERF, you take the half, you see how much lifetime you have, divide by 10, and this is your this is the minimum of TCS/PC you can lifetime you can measure. The other presentation, sorry. So this is how it works. As I said, I will give you the presentation, but this is how we fix our residual. So this is the ERF, and this is the lifetime of your sample. This is how it works, stop, start, blah, blah, blah. This is the explanation of ERF. So it's the pulse, detector, and the electronic. And this is the minimum of lifetime you will calculate. So it's 1 by 10. The largeur à mi-hauteur the case. So this is just explanation about the things. DRF also, electronics, blah, 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 blah. This is the new PPD. And this is just, in the end, it's like a conclusion about everything. This is all the delta diode we have. You can even find it in HORIBA store. And